Hello, dear viewers. In this section, we will present a framework that expands traditional concepts of space-time by incorporating fractal geometry, a perspective deeply rooted in the mathematical study of differentiability and scale invariance. The model poses a profound extension of Einstein's general relativity by challenging the assumption of differentiability at small scales, thus opening new avenues for integrating quantum mechanics with cosmology. At the heart of this theory is the concept of scale relativity, which assumes that the laws of physics must be invariant, not only under changes in position and velocity, as in special relativity, but also under changes in scale. This builds on Benoit Mandelbrot's earlier work on fractals, where the defining feature of a fractal object is its disorder at all scales. This disorder leads to scale differentiation, where more and more complex details continually emerge, seemingly without limit, as one approaches a fractal structure. This is particularly important for space-time, which is characterized as fractal at quantum scales. The concept of scale differentiation underlies the non-differentiable nature of fractal space-time. In traditional geometry, smoothness and differentiability are fundamental assumptions that allow for well-defined trajectories and distances. However, for the microcosm of space-time, we must discard these assumptions. By doing this, it is suggested that at sufficiently small scales, geodesics, or the straightest possible paths in space-time, are no longer smooth, but instead fractal and uneven. This departure from classical smooth geometry coincides with the behavior of quantum particles, which exhibit probabilistic, nonlinear paths such as Brownian motion. The connection established between fractal space-time and quantum mechanics is very important. The quantum field, defined by uncertainty and wave-particle duality, is naturally compatible with the properties of fractals. For example, the Heisenberg uncertainty principle, which limits the precision with which position and momentum can be known simultaneously, reflects the scale distortion in fractals. As a variable, such as position, is known more precisely, its counterpart, momentum, becomes increasingly uncertain or divergent. This divergence is identified with the de Broglie scale, where classical, differentiable spacetime gives way to a quantum field characterized by fractal structure. Above this scale, spacetime behaves classically and smoothly, but below it, spacetime becomes non-differentiable and quantum effects become dominant. This fractal nature of spacetime provides a conceptual bridge between classical and quantum physics and offers a new framework within which both can be described without contradiction. In addition, the model introduces the concept of temporal reversal at small scales. This is important because in classical physics, time generally flows in one direction, forward, due to entropy. However, in the fractal quantum realm, time can behave differently and potentially reverse at certain scales. This suggests a deep symmetry in the fabric of space-time itself, which becomes apparent when we consider the fractal structure, which is not differentiable only at quantum levels. Tim Palmer has proposed the existence of a quantum fractal invariant set, like Nautilé's fractal space-time, which implies that the fundamental structure of the universe is fractal and invariant under certain transformations. The concept of invariant sets in chaotic systems parallels Nautilé's idea of giving up differentiability to gain a more general understanding of spacetime. These fractal models offer a promising direction for combining quantum mechanics, chaos theory, and cosmology into a unified framework. Fractal spacetime challenges the classical concept of time. Instead, time itself may have fractal properties, becoming fragmented and reversible on quantum scales. This could open new avenues for understanding human perception of time and its relationship to the underlying structure of the universe. Classical relativity, developed by Einstein, holds that the laws of physics remain invariant under transformations of the speed or position of observers. In other words, no matter how fast an observer is moving or where they are in space, the physical equations governing phenomena remain consistent. Scale relativity extends this principle by asserting that the laws of physics should remain invariant under transformations of scale, that is, changes in the size or resolution at which physical phenomena are observed. In this framework, the laws of physics should be equally valid whether phenomena are observed at the scale of galaxies or subatomic particles. The basic understanding here is that scale, like speed, cannot be defined in absolute terms. Just as the speed of an object is always measured relative to another object, the size or scale of an object is meaningful only when compared to some other reference. This relational nature of scale is what allows the principles of relativity to be applied beyond space-time transformations to the realm of scaling transformations. This generalization could be crucial to the long-standing goal of unifying quantum mechanics and general relativity because their primary distinction lies in the very different scales at which they operate. Quantum mechanics governs the microcosmic world of particles, while general relativity applies to the macroscopic structure of space-time and gravity. In scale relativity, these different realms are no longer fundamentally separate, but rather different manifestations of the same fundamental laws seen at different scales. Fractals play a central role in the formulation of scale relativity because they naturally represent scale invariance. By definition, a fractal object looks similar regardless of the scale at which it is observed. This self-similar structure makes fractals ideal for describing phenomena that transcend multiple scales, and they offer a continuous but non-differentiable geometry that fits well with the non-differentiable nature of quantum space-time. The concept of non-differentiability is crucial in this theory as it allows for a more general mathematical description of space-time. In traditional geometry, space-time is modeled as a smooth, differentiable manifold, meaning that a tangent can be defined at any point, and rates of change, derivatives, such as velocity or acceleration, can be calculated. However, in fractal geometry, this smoothness is broken, and at every point, the structure is rough and irregular, and therefore non-differentiable. To understand the importance of non-differentiability, let's revisit the concept in a mathematical context. A function is said to be differentiable if it has a well-defined slope, rate of change, at every point on its graph. This slope is determined by the function's derivative. If the derivative exists at every point, the graph is smooth, meaning that velocity, rate of change of position concerning time, and acceleration, rate of change of velocity concerning time, can be easily calculated. However, if a function is not differentiable, it does not have a well-defined slope at certain points, or potentially, as in the case of fractals, at every point. A classic example of such a function is the Weierstrass function, a continuous nowhere differentiable function. The graph of the Weierstrass function shows an infinite number of turning points where the curve suddenly changes direction. Zooming in on any part of the graph reveals more turning points, showing that the irregularity of the graph continues at all scales. This fractal structure makes the Weierstrass function a suitable analogy for fractal space-time, which, like the function, is continuous but not everywhere differentiable. In a physical context, this means that the geodesics of fractal space-time, representing the paths of light and particles, are not smooth curves but rather rough, irregular paths. This reflects the unpredictable trajectories of quantum particles, which do not follow smooth, classical paths, but instead exhibit probabilistic, irregular motions, such as those observed in Brownian motion. Non-differentiability brings a higher level of generality to the description of space-time. Traditional physical theories rely heavily on differentiability, as they provide a means to calculate forces, predict trajectories, and form equations of motion. In classical mechanics, differentiability shows that physical quantities such as velocity and acceleration are always well defined. However, in the quantum realm, the Heisenberg uncertainty principle tells us that certain pairs of physical quantities, for example position and momentum, cannot be known with certainty at the same time. This uncertainty suggests that at the quantum scale, physical trajectories are not smooth and definite, but rather uncertain and probabilistic. These features are well captured by the fractal, non-differentiable structure of spacetime in the fractal spacetime model. The introduction of scale relativity and non-differentiable fractal spacetime provides a potentially unifying framework for understanding the universe at different scales. The self-similar, scale-invariant nature of fractals ensures that the same fundamental principles apply whether we are dealing with the behavior of a particle in a quantum field or the curvature of space-time around a massive object. Furthermore, the intrinsic non-differentiability of fractal spacetime may offer a natural explanation for the apparent randomness and uncertainty observed in quantum phenomena. Rather than viewing this randomness as an indication of incomplete information or lack of determinism, it can be viewed as a consequence of the underlying non-differentiable geometry of spacetime itself. This perspective is consistent with the growing recognition that the classical, regular picture of the universe may be an emergent phenomenon, applicable only at macroscopic scales, and that the fundamental structure of space-time at quantum scales is much more disordered and complex. In a broader context, the fractal model of space-time suggests that the geometry of the universe is neither flat nor merely curved, but is more general, encompassing both possibilities and also accounting for the non-uniform, self-similar structures of fractals. As Lefebvre notes, fractal spacetime preserves the continuity of traditional spacetime, but abandons differentiability, providing a more general framework that can describe both quantum mechanics and cosmology in a unified way. This approach is conceptually similar to how Riemannian geometry, with its curved spacetime, extends Euclidean geometry, which assumes flat space. Similarly, fractal geometry encompasses both Euclidean and Riemannian geometries, but generalizes them to include the properties of convexity and self-similarity found at all scales. It has been suggested that fractal structures can serve as solutions to optimization problems in natural systems, where competing constraints give rise to self-similar fractal patterns. For example, in the case of a tree, a repetitive branching pattern maximizes surface area for light collection while minimizing the volume of the structure. This results in a fractal dimension of between 2 and 3, maximizing the tree's efficiency in converting sunlight into energy. The self-similar repetition of branches, leaves, and veins within leaves increases surface area, allowing for maximum photosynthesis, and demonstrates how fractal structures naturally emerge as efficient solutions in biological systems. This optimization process, where a system balances competing needs, can be generalized to other fractal systems in nature. Notal describes fractals as the balance between divergence and finiteness, a concept that can be understood by looking at the Mandelbrot set, a well-known fractal. At the boundary between divergence, infinite complexity, and finiteness, stability, a fractal constantly oscillates, creating an edge where complexity constantly emerges. Nautilus draws on the concept of the edge effect, a term from permaculture that describes how increasing complexity and abundance emerge at the boundary between two ecosystems. For example, the edge of a pond hosts more diversity than the center or surrounding area of the pond, as the interface between water and land creates a zone of increased resources and opportunities for diverse life forms. In this context, fractals emerge as a structural embodiment of this boundary complexity, continually revealing new details as we approach the edge. The edge effect in permaculture can be metaphorically extended to describe how life on Earth exists at the interface between matter and light, time and timelessness. This concept evokes profound philosophical and physical insights. Matter, governed by time, interacts with photons, which experience timelessness as they travel at the speed of light. At this intersection where time and timelessness meet, life manifests and evolves as fractal structures continually emerge at the edge of different systems. Water, in particular, plays a key role in this dynamic tension between the Earth and the Sun. As it rises toward the Sun through evaporation and falls back to the Earth through precipitation. Plants, on the other hand, adopt fractal forms, maximizing their interaction with both the Earth and the Sun by increasing their surface area and optimizing the capture of sunlight while maintaining the structural integrity necessary to support life. This optimization of surface area through fractal density reflects the efficiency underlying the fractal patterning of nature. A photon traveling at the speed of light, as discussed earlier, does not experience the passage of time. Matter, in contrast, is firmly embedded in time. The interaction between these two realms, the temporal existence of matter and the timelessness of light, creates a dynamic boundary where complexity emerges. This interaction between time and timelessness becomes particularly interesting when considering the role of the human brain. It has been suggested that the brain may serve as a site where this interaction is particularly pronounced, perhaps through quantum processes that blur the lines between time-bound experiences and the timeless nature of quantum superposition. As with the Mandelbrot set, the boundary between wave and particle thought and body, or superposition and collapse, needs to be explored more deeply. By exploring these fractally structured boundaries, whether in nature or in our understanding of time and the universe, we are in the process of unraveling complexity and revealing deeper levels of structure. In this sense, exploring fractals is like exploring the boundaries of our understanding of nature, time, and the cosmos. The repetitive patterns found in nature, whether in the branching of trees, the distribution of ecosystems, or the interaction between matter and light, reflect the fractal structures of space-time proposed in the theory of scale relativity. Fractals serve not only as mathematical models, but also as the fabric of nature, optimizing processes, increasing complexity at the edges, and connecting the microcosm to the macrocosm. The concept of temporal reversibility arises from the interpretation of virtual particles and antiparticles. It is a fundamental idea in quantum field theory. Virtual particles are known to move in and out of existence, moving both forward and backward within the quantum field. It is possible to take this concept even further by suggesting that the many different particles we observe may be a single particle bouncing back and forth in time. Within its framework, a particle can traverse time, moving forward in some cases and backward in others, appearing as both a particle and an antiparticle. We can view the particle oscillating through time, alternating between forward and backward motion. Or we can take a slice of time by observing only certain moments. From within one of these time slices, multiple particles can appear to exist at different times, even though they represent the same particle moving back and forth in time. This model is striking because it challenges our everyday understanding of particles as separate entities moving in a single direction through time. Instead, it suggests that on very short time scales, temporal reversibility is possible, and the distinction between particles and antiparticles disappears. A fundamental feature of the model is that, on quantum scales, a particle's proper time becomes scale-dependent. Proper time is the total time a particle experiences along its world line, its path through space-time. But in a fractal framework, this time decomposes as we measure it at smaller and smaller scales. This scale decomposition, a feature of fractal systems, mirrors the uncertainty we encounter in quantum mechanics, where smaller temporal measurements lead to increasing uncertainty in energy. This connection to the Heisenberg uncertainty principle is central to the argument. As the uncertainty in time, delta t, decreases, the uncertainty in energy, delta E, increases. This relationship is governed by the time-energy uncertainty principle. As we try to measure time more precisely, the energy involved becomes increasingly uncertain, giving rise to virtual particle-antiparticle pairs. The differentiation of energy on quantum scales is inherently fractal and is used to argue that a particle's proper time includes all the forward and backward paths of both particles and antiparticles in time. This leads to the idea that at the smallest scales, space-time itself becomes fractal, characterized by non-differentiability and self-similarity. At this point, proper time begins to split, a clear indication of the fractal nature of time at very small scales. This transition represents a transition from the classical definition of time as a continuous, uniform dimension to a fractal definition, where time becomes fragmented and scale-dependent, similar to the structure of fractals such as the Mandelbrot set or the Julia set. Notal's calculations suggest a temporal transition from dimension 1, non-fractal, to fractal dimension 2 around de Broglie time, which is given as follows. At this point, proper time begins to separate into fractal patterns similar to those we observe in two-dimensional sets, such as the Peano curve. This transition suggests that time itself becomes fractal on quantum scales, filling space in the same way that fractals fill planes in mathematics, creating infinite complexity at smaller and smaller scales. As time becomes increasingly fragmented and complex at smaller scales, this fractal dimensionality serves as a natural model for describing the underlying structure of quantum space-time. Just as fractals reveal more detail as we zoom in, time exhibits increasingly complex behavior as we measure it at smaller and smaller intervals. The self-similar nature of fractals means that this complexity repeats itself at every scale, suggesting that quantum time may follow a similar pattern, with smaller and smaller units of time revealing greater variance and uncertainty. As we explore the quantum realm, time itself becomes timeless, exhibiting reversibility and self-similarity. Thanks for listening, and take care.